and welcome to Late Nights with Mrs. Gutenberg.
Hi, guys. So I hope you're all doing well. I hope that you are keeping up with forces and that hopefully it's making a little bit of sense to you, judging from how you're doing on some Edulastic assignments. It looks like some of you are getting the hang of it, so hopefully going over these force diagrams and net force and calculating net force and determining if something is balanced or unbalanced will be really helpful to you. So I'm going to kind of go over the paper that you were supposed to do yesterday, or I said you could hold off and kind of wait until I was had this video posted and you could kind of go through it with me. So I'm going to kind of go back and forth between the computer screen and then I'm going to draw out the force diagrams here. So for each problem, we're going to draw a free body diagram, we're going to calculate the net force, and we're going to identify whether the force is balanced or unbalanced. So here we go. So I'm going to start with the first example. So Mrs. Gutenberg lifts a heavy box over her head with one push of the arm and a force of 250 newtons. Gravity is pulling down the box with a force of 200. All right, so if you remember, you always represent the object with a box. So for example, this box would represent a heavy box that I would be lifting over my head. So if I'm lifting the box over my head, I'm pushing up on the box. So my arrow is going to go up, and I'm going to label it F applied, because a push or a pull is an applied force. And then the value of that force is 250 newtons. Okay, if you put the arrow underneath pushing up on the box, that's okay as well, as long as your arrows are going in the right direction. And then the other force, gravity is pulling down the box with a force of 200 newtons. So this would be F gravity. And I would want to make my arrow a little bit smaller because the force is less. So it's pulling down with 200 newtons. So there's my free body diagram. And then it says calculate the net force. So remember, if arrows are going in the opposite direction, okay, you subtract. And if arrows are going in the same direction, you add them. Right? So basically net force is what's the total force acting on this object. So my arrows are going in the opposite direction. So to find my net force, it would be 250 newtons minus 200. So my net force is 50 newtons. Okay, and remember, force is something called a vector, right? So it has to also include a direction. So in this case, 250 is greater than 200, so the direction is up. And then part 3 is the force balanced or unbalanced. So if the forces were balanced, my net force would equal 0. But since I have a net force, it's 50 newtons up. My forces are unbalanced. So the box is going to move up. So there's our first example. All right, so let's go into the actual problems. So 2 science students are pushing a box, one on each side of the box. So I'm going to draw the box on the paper. Mason is pushing the box with a force of 10 newtons to the left. So Mason would be pushing this way, so I'm just going to draw the arrow on this side pointing to the left. And again, it's an applied force. It's Mason. He's pushing. And the force is 10 newtons. Riley is pushing the box with a force of 15 newtons, so he's pushing with more force, so I'm going to make my arrow a little longer. And again, it's an applied force because it's a push. And that is 15 newtons. Okay, now if I was going to include all of the forces in this diagram, I'm also going to have gravity pulling down on the box. And then if you remember, if the box is sitting on the ground, there's also going to be the normal force that would be acting in the opposite direction of gravity so that the box could sit in one spot. And then we could add friction, but really I'm most concerned that you have these two forces right here, the ones they're talking about in the problem. We have the applied force of Mason pushing to the left and Riley's pushing to the right. So our arrows are in the opposite direction. So remember, if they're opposite, we want to subtract. So my net force is going to be 15 minus 10. So I'm going to get 5 newtons, and the force that's winning is going to be the one that's pushing to the right, which is Riley. So it's going to be 5 newtons to the right. And again, if I have a value for net force, my forces are unbalanced. So the box is going to move to the right. Okay? All right. Next one. A book is at rest on the desk. So here's my book at rest. The book has a weight of 10 newtons. So, and I said hint, weight is a measure of the force of gravity. So gravity is pulling down with 10 newtons, right? However, the book is at rest, so it's not moving. So if you remember when you learned about the types of forces, the normal force is the force that works in the opposite direction of gravity. So the normal force is pushing up on the the book. So if gravity's pulling down, the normal force is pushing up. If it wasn't, the book would fall through the table, but it's sitting on the table, it's at rest. So the normal force has to equal the same amount as the force of gravity because it's at rest, it's not going anywhere. Okay, so my net force, the arrows are in the opposite direction. So I subtract, so 10 minus 10, the net force is 0 newtons. So if my net force is 0, the book is not moving, my forces are balanced. Okay? All right. And you are more than welcome to fast forward, pause, freeze, whatever you need to do to kind of help you with these problems. All right, number 3, Bobby applies a rightward force of 20 newtons on the book. So my box is the book. Okay, Bobby's applying a rightward force, which means he's pushing to the right, or it doesn't really say, it could be pulling to the right. So it's going to the right, and it's an applied force. And it has a value of 20 newtons. Okay, there is an opposing force of 5 newtons on the book. So that force that's opposing the motion of the book, okay, hopefully you can recognize that that is friction, right? If I'm sliding something across the desk, there's going to be some friction there, and that's going to be 5 newtons. Okay, so our arrows are in the opposite direction, so the net force is going to equal 20 minus 5, so 15 newtons, and remember we have to include a direction, so 20 newtons is obviously stronger than 5, so it's going to go to the right. And then since we have a value, our forces are unbalanced. That's why the book is moving across the desk. All right, number 4, Braylon carries his backpack up on his shoulder. The pack is suspended motionless with one strap from one shoulder. So this one doesn't have values of force, but it says the pack is suspended motionless with one strap. So you can picture this is a book bag and it's hanging from your shoulder with one strap. So the force that would be pulling that down would be gravity. Okay, and then the force that would be holding it up, it's a strap. So if you remember the different types of forces, a strap, a rope, we would call that tension. Okay, and then the key word is that it's motionless. So if it is not moving, we know that our net force has to equal 0 newtons. And if our net force is 0 and it's not moving, then we know our forces are balanced. All right, number 5, a skydiver is descending toward Earth in free fall with constant acceleration. Ignore air resistance. The skydiver has a weight of 400 newtons. So the box is the skydiver. Okay, it says ignore air resistance. So air resistance would be, like if a feather falls, it's going to fall slower than a brick because the feather's going to catch the air. We're going to ignore that because if there's no air resistance, everything's going to fall at the same rate. It would hit the ground at the same time. So the skydiver has a weight of 400 newtons. So his weight is gravity. Okay, it's pulling him down with 400 newtons, and there is no other force. He is just accelerating toward the ground. Okay, so if there's no other arrow, our net force equals 400. And because we have a net force, it is unbalanced. And remember, force has to have a direction, so 400 newtons down. All right, number 6. The skydiver has now opened his parachute, increasing the air resistance, excuse me, and slowing his speed. So here's my skydiver again. Now I've opened the parachute, so if you know what a parachute is, right, there is a strap. So you could represent this a couple different ways. Like usually a parachute would have 2 straps hanging from it, right? So you could label those tension and then gravity is still pulling down. And this one doesn't have any values. We know gravity's pulling down with 400, but we don't know how much the air resistance was increased, okay? Or you could draw it if you just want to talk about air resistance, right? There's another way you could do this. Gravity's pulling down, but air resistance is acting in the opposite direction, but still gravity is going to be a longer arrow because he's still going to keep falling. All right, number 7. Mrs. Holland and Mrs. Nemeth are playing tug of war against Mr. Sakamoto and Mr. Sievert. Draw a force diagram that illustrates Mrs. Holland applying a force of 75 newtons to the right. Okay, so I'm just going to go through. So here's our box. It's representing the rope. Mrs. Holland is applying a force of 75 newtons to the right. Now, if I'm thinking tug of war, that means she's pulling. So she's going to the right, 75 newtons. And that's Mrs. Holland, so I could even label this Mrs. Holland. And Mrs. Nemeth is pulling to the right with 45 newtons, so she's not as strong. And so the arrow's going to be shorter, so 45 newtons. That's Mrs. Nemeth. Okay, and then Mr. Sakamoto is 85 newtons to the left. So his arrow is going to be the longest. So that's Mr. Sakamoto. And it's 85 newtons. And then Mr. Sievert is the weakest. Not really, but in this problem he is 30 newtons to the left. So that's Mr. Sievert. Okay, and those are all applied forces because they're all pulling forces from people. So calculate the net force. So this one is a little bit trickier because there's more forces. So these 2 arrows are acting in the same direction. So we're going to add them. So 85 plus 30 is what? 115. So we'll say 85 plus 30 is 115 newtons. Okay, so that's the total force from Mr. Sakamoto and Mr. Sievert going that way. Mrs. Holland and Mrs. Nemeth, so 75 plus 45 is also 115, correct? Hold on. 8, 12, oh no, 120. Okay, so 75 plus 45 is 120 this way. So we added these together and these because they're going in the same direction. Okay, so now we have 115 newtons to the left, 120 to the right. So we need to subtract those two to get the net force. So net force equals 120 minus 115. So we get 5 newtons, and the winning force is going to be to the right. And then if I asked you if they were balanced or unbalanced, because there's a net force, you would say that they are unbalanced. So Mrs. Holland and Mrs. Nemeth would be moving the rope in their direction. All right, couple more. The 5 children picked up a rope in the park and decided to play tug of war at the exact same time. Predict the motion and provide a force diagram to support your prediction. All right, so we're going to draw a box. It's another tug of war. We've got 50 newtons this way and 50 newtons. Okay, and then on the other side, we've got 30 newtons, 30 newtons, and 40 newtons. So make that a little longer. Okay, so these get added together. So we're going 100 newtons this way. These get added together because they're going in the same direction. So 100 newtons this way, okay? So if my forces are this in the opposite directions, remember I subtract to get net force. And the net force is 0 newtons. So those forces are balanced. That rope is not going to go anywhere because the net force is 0. All right, we need to take a timeout. I'll be back with the rest of the video later. See ya.